At the inception of the universe, equal amounts of matter and antimatter were created. But if this remained true, we simply wouldn't be here. We know this due to the well-established fact that when matter comes into contact with antimatter, they destroy one another, leaving nothing tangible intact. Yet here we are, and so what imbalanced process allowed for matter to claim dominion over antimatter in the early universe? We think that particles called neutrinos may hold the key to unlocking this mystery. See, neutrinos are really strange, coming in 3 distinct types and with the ability to shapeshift from one kind to another as they travel across vast distances. To determine whether neutrinos and the antimatter twins do in fact change their identities in unequal measure, Fermilab will host a future experiment with the world's most intense neutrino beam called DUNE, to see how these particles behave as they travel between Illinois and South Dakota. But there is a problem, which is that neutrinos are incredibly elusive. If you were to propel 1 billion neutrinos towards a block of lead that is a light year thick, a distance equivalent to traveling to the moon and back about 10 million times, only 1 or 2 would ever collide with an atomic nucleus living inside of this enormous trap. Now, imagine you are trying to track the total number of leaves falling from trees on a windy day by capturing them into a bucket. Even if you are incredibly fast, ultimately many of them will never be caught. But keep in mind that if you know how many leaves typically fall outside of your bucket, you can still accurately account for any that are missing. Now, when neutrinos do collide, for example inside of another Fermilab experiment called MicroBooNE, the result is some very intricate images. My research involves analysing these images to extract something that we call the neutrino cross-section, a quantity that tells us how often the neutrinos like to collide with or completely avoid the atomic nuclei inside of our detectors. So just how, given enough information, we can accurately reverse engineer the total number of leaves, we can use the information about the neutrino cross-section to tell us how many neutrinos or antineutrinos the DUNE experiment should see as they shapeshift on the 800-mile journey. Any hint of imbalance, and we are one step closer to understanding the cosmic asymmetry that has ultimately led you to be watching this video today, 13 billion years after the inception of the universe.